The DCIL Presents series, which this is part of, is a collection of webinars and events that are designed to educate and raise awareness around virtual currencies. And today I'm very excited to have Nathaniel Harmon of Blockchain Solutions Hawaii as our featured speaker. Now, Nathaniel was the first person to reach out to me when this first series began earlier this year, and I'd been looking forward to hearing from him ever since. A couple of housekeeping points before we get started, though. One, this session is being recorded and will be sent to those who have registered for this webinar as well as distributed elsewhere. Two, you are welcome to send in your questions during the session through the Q&A function. We will address them when appropriate or during the Q&A portion of this webinar if we have time. So without further ado, I would like to encourage and welcome Nathaniel Harmon, founder of Blockchain Solutions Hawaii, to join us here. And Nathaniel, thank you for joining us, and take it away.
Thank you, Ryan, and I'd like to say thank you to HTDC and all the acronyms. And I think I'm in need of a new headset. Okay, let's go ahead and share my screen here. All right. Think everybody can see this now. Yeah, so my name is Nathaniel Harmon. I received a master's degree in Marine Geochemistry from Manoa. And after my time at I founded Blockchain Solutions Hawaii. So this is kind of a love child of both of my passions. BSH, we are a Bitcoin development company. And if you can think of Bitcoin as like the internet, we build the Bitcoin equivalent of websites and private internal networks for businesses, just like your internet service provider does for you and your business. We offer asset security consulting through our zero knowledge, non-custodial security programs, where we help businesses and individuals safely self-custody their own assets. And we do general business and integration and consulting. And, just as we're going to do today for the energy industry, we can help examine if and how Bitcoin can help improve productivity and efficiency in your industry. Before we move on, it's important to understand what this is not. This is part 5 in this series. And so we're not going to do a Bitcoin 101. We're going to skip that. That's been done, I think, twice now. And we're also not going to engage in a subjective discussion on what is and is not a productive use of energy. Some people think billionaires going to space isn't a productive use of energy, but it's not really my prerogative to tell them what to do. And we're also not going to do a just direct comparison between Bitcoin's energy use and other industries like the traditional financial industry, because again, that all comes back to a subjective discussion of what you personally believe is a productive use of energy. Instead, this is an energy talk. So we've split this talk into 2 parts. Part 1 is going to be about energy. So we need to give some background into energy economics, how Hawaii gets and uses its energy, and the 2 major issues facing Hawaii's 2045 carbon negative goal, those being curtailment and our firm supply problem, which I like to refer to as the Oahu problem. In part 2, we're going to talk about Bitcoin, give some background about how Bitcoin mining works, and we're going to do a little bit about mining economics. And I hope by the end of this presentation, we can objectively answer the question, does or can Bitcoin help or hinder our energy issues and goals? So just some basics on energy economics. With fossil fuels, we kind of know instinctively that the capital expense is going to be less than your operational expense. If you go down to Hardware Hawaii and buy a small generator and you're running it all day, every day, you know that the cost of the fuel to power that generator is going to be greater than the cost of that initial cost of the generator, your CapEx. Renewables have the opposite. So it's really expensive to build this infrastructure, but once it's built, well, the wind blows for free and the sun shines for free. Now, there are two types of renewable energy. There's dispatchable and non-dispatchable. Dispatchable are going to be things that supply your base load, firm supply. It's always there, regardless time of day. So things like geothermal, hydropower, and more controversially, nuclear. And they have an economy of scale. So the larger you build them, the plant size, the larger you build the plant, the cheaper the cost of energy. The smaller the plant, the higher the cost of energy. And with dispatchable, just like any dispatchable firm source of energy, you build capacity for an anticipated future demand. You don't build a power plant for the energy you need today. You build a power plant for the energy you're going to need in 20 years. Now, for fossil fuels, this isn't a problem. You simply don't burn that extra fuel, and it doesn't affect you. But with dispatchable renewable energy, well, the geo is still thermaling and the river is still flowing. So what this leads to is idle capacity. And once you have that idle capacity, that's pushing you back up the hill, leading to higher energy costs. Now, your non-dispatchable sources, things like wind, solar, waves, these are intermittent sources. They're not always available to you. So, the wind's not always blowing, the sun only shines half the day. And that means you're going to need to store that energy, and you're going to need a smart distribution system. And of course, that ends up with higher energy. And, these non-dispatchables, they also have a bit of an economy of scale, but a solar panel only puts out so much energy. If you want more, you need to buy another. So it's not nearly as pronounced, but you do get, some discount for scale. So how do we in Hawaii consume energy? Well, residential consumes about 11% of our total energy consumption, commercial 14%, industrial 18%, and the vast majority of our energy consumption comes from transportation, all of which is fossil fuel based. You can see the split between ground, air, and marine here. Now, producing energy, so not including transportation. You can see the breakout of how we produce that energy here. And if we want to reach our 100% renewable goal by 45, that means we're going to need to replace the 75.2% of production from coal and petroleum. And if we want to electrify our ground fleet, we're going to need to adjust that. We're going to need to find that extra energy for ground transport. So when you adjust that, we need to replace 84% of our production with renewable energy. Now, where do we get that energy from? In 2019, our renewable production is about 20.3% of all of our production. So this doesn't include transportation. Now, we get that from our dispatchable sources. Our base load is going to be mostly from bioenergy. So that's going to be things like biofuels, municipal solid waste, or as it's colloquially known, trash. And we get a little bit from hydro. We get, but the vast majority of our renewable production comes from just our non-dispatchable sources, so solar and wind, with distributed PV or rooftop PV far outclipping the rest of them. And relying so much on non-dispatchable sources has led to two problems: curtailment and firm supply. So to start with the curtailment problem, this is a supply and demand issue. In the middle of the day, when the sun is shining and the wind is blowing, the supply of energy is greater than the demand, the load. And this leads to waste energy, excess energy in the system that can cause problems. Now, in 2020, the state of Hawaii curtailed around 56 gigawatt hours of energy. If that had been sold on the grid at around 30 cents per kilowatt hour is what I pay, that would equal about $20 million worth of lost revenue. Maui alone made up the vast majority with 51 gigawatt hours. And, if you live on Maui or the North Shore of Oahu, you oftentimes see the windmills not turning, they turn them off. And of course, the utility pays for this curtailed energy to maintain a reserve supply. But they don't pay the 30 cents that we pay. They pay around 10 cents per kilowatt hour based on some of the power purchase agreements I've seen and the one I personally have. And the dilemma here is that the more renewable energy we produce, the cheaper the energy cost should be. But that curtailment leads to higher energy costs for everybody, and it gets, added to our bill, and we end up paying for it. So why can't we just simply store it? We're spending money to throw energy away. So why can't we just store it for later? This brings us to the firm supply problem, or as I like to call it, the Oahu problem. The firm supply on Oahu is around 1,800 megawatts. All the other islands have around 200 megawatts or less each. So this has led our energy companies, the HECO family, to conclude that even with an abundance of renewable energy resources, the power system must have a complement of firm dispatchable thermal resources. These thermal resources will be fueled by liquefied natural gas. But why? Why can't we just store all this extra energy for later? And this comes back to something called the capacity value. And we can see the capacity value of our wind and solar resources here on Oahu. And essentially what capacity value is how much demand can an energy resource reliably meet. For centralized solar, it's around 6.1%, distributed PV, 1.9, wind, a little better, 16.8. So to put this in perspective, what new capacity of a renewable resource would be required to meet 100 megawatts of load? If we wanted to use centralized, solar, we would need 1,600 megawatts of capacity in order to meet a 100 megawatt load. For distributed, it's much worse. It's 5,200 megawatts. And for wind, it's around 6x, so 6 times. And we understand how this works. If you are using all the energy that a solar panel is putting out, you have nothing to store. So how much more do you need? And what does this look like if we tried to replace all of Oahu's firm supply with non-dispatchable sources? So, I live on Oahu, and one of my favorite dive spots and snorkel spots is over at E Beach. So let's talk about our favorite power plant, the Kahe plant, at around 650 megawatts, which is about a third of our firm capacity. Now, we clearly don't have enough land for the wind farm, so let's look at offshore wind. With a capacity of around 16.8%, that means we're going to need 3,800, almost 3,900 megawatts to replace that 650 megawatt power plant. And if we look at a recently developed offshore wind farm using their, the same turbines at this energy density and cost that they got, we find that we would need around 553 turbines that would take up a total area of 1,600 square kilometers, which is just slightly larger than the island of Oahu at a cost of around $19 billion. And once we add in the battery cost, you end up with a total cost of around $20 billion. So essentially, we would need to bulldoze the entire, ocean floor between Oahu and Maui and more 550 turbines in order just to replace a third of our firm capacity. Now, if we tried to do this with centralized solar at a capacity of 16.1%, we would need around 10,600 megawatts. And if we use the top of the line models that are available from First Solar, these are the utility scale modules, we would need 31 million solar panels taking up a total area of 80 square kilometers, and that looks like this little square here. And that's, of course, with no space in between each panel and some sort of trellis system to repair and clean them. The cost for the PV alone, not including the land cost, would be around $3.5 billion. And of course, you still have to buy the battery, so around $4.5 billion. Now, producing this much energy to fill up all of this storage is going to generate even more curtailed energy than we already have. So this is going to be a problem no matter what the non-dispatchable source we use. Moving on to part 2, Bitcoin. So just to quickly address some of the criticisms lobbied at Bitcoin at yesterday's congressional hearing, there is a myth that one transaction using the Bitcoin network consumes the power of an average US household for around 60 days. This is, like I said, just a myth. Right now it's producing 6.25 new Bitcoin consumes an average US household of 60 days. In fact, yesterday alone, I sent 100 transactions without doing a single one, taking up anywhere close to 2 months worth of energy. And you can think about Bitcoin similar to how gold is. It takes a lot of energy to dig the gold out of the ground and then refine that gold. But once you have that gold, handing it to someone else doesn't take nearly that amount of energy. In light of the conversation yesterday on the Hill, it's important to understand that Bitcoin is unique and it is in a class of its own. And lumping Bitcoin together with other cryptocurrencies is rather disingenuous, and it should be spoken of as a separate thing. And you hear oftentimes people talking about, oh, I really love blockchain technology, just not Bitcoin. Well, blockchain technology has been around for 30 years or so, and they found no use for it because it's just a database. In fact, it's a not as good database as, a SQL server. It wasn't until Satoshi Nakamoto, the inventor of Bitcoin, tied the proof of work with a blockchain. It just so happens that a blockchain is the perfect way to record that proof of work. And I'm not going to get into this, but I solicit questions for answering during the Q&A. That proof of work, especially Bitcoin's proof of work, cannot be replaced with a proof of stake system and is much better for many reasons. And I'd love to get into that. But what is proof of work? It's referred to as Bitcoin mining. And, when you hear about Bitcoin mining in the media, they often say it's a bunch of computers solving a really complicated math problem. And this is an effective analogy for a quick conversation, but it's inaccurate. The better analogy would be that Bitcoin mining is a bunch of computers playing the largest game of needle in a haystack, and that needle being new Bitcoin. So the needle is randomly hidden in the haystack, okay? And all these computers are just looking around for it, and as soon as one finds the needle, they digitally hold that needle up for the rest of the players to see. The other players will inspect the needle. It's very easy to prove that the computer found the needle, and then the game resets itself because all the computers agree, okay, I've seen you found the needle. The needle is now not in the haystack, so there's no point in continuing to look. And in other words, this is the proof of work. It is easy to prove, but very hard to do. And the haystack size is adjustable. It's automatically adjusted based on a 10-minute game time. The idea is no matter how many players are playing, a game of needle in the haystack, Bitcoin mining, should take on average 10 minutes. So if the needle is being found in 9 minutes, the haystack will get larger, if it's being found in 12 minutes on average, the haystack will shrink. Now, just like this guy sitting here looking through this haystack, you know, he needs some water, he needs some food, he needs energy to keep looking. Just like he needs energy, the computers need energy. So the larger the haystack, the more energy is needed. That energy is the security behind Bitcoin. The energy expended and recorded on the blockchain, that is the security behind Bitcoin, because in order to attack Bitcoin, you would have to expend that same amount of energy. And you often hear criticisms of Bitcoin that Bitcoin isn't backed by anything, but that energy is the backing of Bitcoin. And it is, of course, the largest proof of work system created. It's also the most secure database that we have on planet Earth. So just some basics of energy economics on Bitcoin mining. Bitcoin mining is all OPEX. When done at scale, the cost of the machines is almost irrelevant compared to how much energy you have to supply to power and then cool them. They are effectively space heaters that, you know, search through the haystack. And then they get really hot and you have to cool them. So this means that your profits from Bitcoin mining are solely dependent on the cost of energy. And you'll notice that this, the OPEX being greater than the CAPEX, mirrors renewable energy. So it's the exact opposite, providing a nice complement. Bitcoin mining in 2019 used around 61 terawatt hours of energy, which is around the same amount of energy that PC gaming worldwide used. And looking at a map of major Bitcoin mining regions, you'll notice a trend that Bitcoin mining naturally gravitates to regions with cheap energy, so places with lots of oil, lots of coal, and then lots of renewable energy, Iceland, the Pacific Northwest. Now, when we look at a breakout of it, you can see that in that same interesting bifurcation. You see a lot of these regions with very high renewables, and you see regions with very low. So in 2019, Bitcoin's renewable penetration, or the percentage of energy that powered the Bitcoin network coming from renewables, was around 38%, which was, of course, higher than Hawaii's. And you may have heard that recently China banned Bitcoin. This is true. And if you look at the average for the rest of the world and the average for China, well, China's Bitcoin mining operation was actually dragging the rest of the Bitcoin's renewable percentage down. So now that China has banned Bitcoin mining, the estimate is closer to around 50% renewables. But before they did ban Bitcoin mining, there was this interesting phenomenon called the Great Bitcoin Migration. So there's two major mining regions, or four, but broken up into two. There's the mining in the north and mining in the south. During the winters, all the Bitcoin miners would be located in the north, in Inner Mongolia and Xinjiang, to get access to free cooling, so cutting their operational expense by using the cold weather, and cheap coal energy. But during the rainy season, these Bitcoin miners would physically pack up their data centers, their Bitcoin data centers, and then physically move them south to the Sichuan and Yunnan provinces, where they had access to ample hydro power. You know, these regions are known for the dams that were built there. And during the rainy season, there's so much water flowing that they just have all this excess electricity. And because they built these power plants for demand in the future. But there's no one to buy that energy at the moment. So it would just go to waste. So these Bitcoin miners performed an important service in those areas, in those provinces, as the ideal buyer of last resort. If you have more energy than you can consume, Bitcoin miners will come in and they will guarantee a dispatchable demand. They will guarantee that 100% of your energy production generates revenue, but they're probably not going to pay the same price because it would be wasted. And the idea is that any revenue is better than none if you're just throwing it away. Now, so let's see if we can apply the ideal buyer of last resort to our curtailment issue. By definition, our curtailed energy is waste and has a zero marginal cost to it. So let's see what would happen. So I look at Bitcoin mining as a demand-side solution to our curtailment issue. So we built an economic model and we modeled it. Just going with Maui's oversupply, there's different types of curtailed energy, and we're just going to go with the oversupply from Q1 2020 through Q2 2021. Now, of course, we're going to subtract cooling costs, and we're only going to be mining half the day based on how efficient the solar panels are based on the day. And then, of course, mining is a Poisson distribution, but if you want more information on that, please contact me afterwards. Just to keep things simple, we just plotted the average. And we use the average power purchase agreement from independent power producers at around 10 cents per kilowatt hour, meaning that the power company, MECO in this case, paid around $6.75 million to throw energy away. Now, what if we had taken that energy and instead of throwing it away, we had mined Bitcoin with it? Now, I've identified two strategies here, and let's talk about this graph. So the blue line here is going to be how much money MECO paid, right? This is that $6.75 million over the 5 quarters here. And the first strategy is if they had mined Bitcoin with that excess energy instead of throwing it away, and then as soon as they mined that Bitcoin, immediately sold it on the market. So Bitcoin sold at the time of production. If they had done that, the revenue would be around $8.77 million. That would be this green line. So it would have been profitable for MECO to mine Bitcoin with the excess energy rather than just paying 6.75. And, even if we, even if it's less, even if it came out to be less, it wouldn't matter because anything is better than nothing. And, this $6.75 million is getting added to our energy bills. Now, my favorite method is the HODL method, where once you mine that Bitcoin, you hold on to it. And why would you do that? Well, having an asset like Bitcoin, you can generate interest, you can loan it out. There's all sorts of strategies to generate an income based on just simply holding Bitcoin. Now, I checked the price this morning. I don't know what it is right now, but I checked the price this morning is around $39,000. And if they had held Bitcoin, instead of just selling it, that would be this orange line. It stops here at around when the price is around 60,000. But if they had just held that Bitcoin, and the price today, this morning, would have been around 23 million. So the HODL method would have guaranteed them or provided them, almost 3x what they would have paid for that energy. So now, what's interesting is that even you can combine our storage. We're building a lot of storage, and you can combine that storage with existing curtailment forecasting models, and you can extend that mining through the night. If you know you're going to have if your storage is full, your batteries are all full, and you know you're going to have curtailed energy tomorrow, you can trickle that energy out of the batteries, and now you can mine all day, making you even more profitable. Yeah. And this is a problem, this curtailment is a problem that will affect all islands. So, this brings us to the Oahu problem. We can get to 100% renewables on all the other islands. But as I showed in part one, we just don't have the land on Oahu to solve it. So in order to solve this problem, what are our options? Well, clearly nuclear is not going to work. Not that it's not safe, not that thorium isn't interesting or safe. You still have to have fallout zones, and well, we're on an island. Now, bioenergy is the most, it seems like the solution that they're gravitating to, but bioenergy is a carbon-based source. It's uncured fossil fuels that just hasn't been buried for a long time. And the claim is that, of course, that bioenergy is carbon neutral, but, burning trash here and planting a tree somewhere else, that's creative accounting, and we don't have that luxury at the moment. And, to take a quote from a review paper, Environmental Sustainability of Biofuels, a review from the Royal Society, the greenhouse gas savings for most of the feedstocks for bioenergy are simply not sufficient. And when you look at the land use changes, the nutrient problems, the loss of habitat, ecological disruptions, the production and the transportation, it's certainly not carbon neutral. Now, we have a lot of geothermal energy. Sure, the Big Island has quite a bit, somewhere in the range of 500 to 1,400 megawatts. Maui has around 40 to 140. So clearly Maui doesn't have enough to solve the Oahu problem, even if we do tie them together. And, we could, in theory, tie the Big Island to Oahu, but looking back at comments from the 90s, the political palatability of this is suspect, whether it'll get done or not. And, how would we pay for it? It's a massively expensive cable, and you could just exploit all the energy on the Big Island and mine Bitcoin until you could pay for the cable. But again, I don't think that's going to fly, especially with all the protest around Puna. Hydropower, there is some hydropower, just not on Oahu. Now, Kauai is doing an interesting thing where they are pumping hydro. So they're pumping water uphill. They built a lake. They are pumping water uphill and releasing that. That's a storage technique. And you're still going to have, of course, curtailment problems. And, on Oahu, which mountaintop are we going to remove? And, there's a lot of not in my backyard here. Now, when I look at the state, I don't see land. And that's really the problem with the Oahu problem, is that we just don't have the land. So I see ocean. So what are our ocean resources that we have available? Well, wave comes to mind, but from a study from HNEI, the Hawaii Natural Energy Institute at UH, they concluded that even if we cited all the shoreline segments, you'd only get about 17% of Oahu's energy requirements from wave. So having wave farms all around the island. And again, wave is an intermittent resource, so you're still going to need to store it. There's another source of energy. It's called OTEC. And in theory, OTEC does have the potential to supply 100% of Hawaii's energy needs. The challenge with OTEC is that there's no prototype operational data. And so far, OTEC, the real problem is that so far, OTEC has struggled to demonstrate profitability. And that profitability would be further exacerbated by the need to curtail that energy. Just based on our distributed resources. If they can't sell it, it's going to be even less profitable. But what is OTEC? So OTEC is a older technology. It's been around for a long time. It was first proposed in the 1880s, so it's around 150 years old. It's not a new idea. And the first plant was built in the 1930s. And essentially it works as using the surface ocean as a giant solar battery. What you can do is you can generate energy on the difference in temperature between the warm surface water and the deep cold water. You know, we live on a volcano that gets deep pretty quickly offshore, so we have access to deep water close to shore, and this is a zero emission firm supply. And it can be floated. So you're not mooring these things, it's not like a windmill where you have to moor them, but they're floating facilities. So you can stick them 10 miles offshore, and they're about the size of a container ship. And it's interesting, you know, you connect them by a single power cable. Now, it's interesting that Hawaii does lead the world in OTEC research. Mackay Ocean Engineering, located here on Oahu at the Mackay Pier. They have been testing this for decades now. They even built the first of its kind grid-connected testing facility on the Big Island. It's only 100 kilowatts, and it's used for testing the heat exchangers and pumping. And but yeah, it's been, you know, working since 2015, and it's very interesting. Now, there's no prototype operational data, and why? Well, the answer is the economy of scale. So you have to build a small plant before and show that it's, you know, prove that it works and prove that it's profitable before you can go and build the large ones. But because it's an economy of scale, these small plants are never profitable. You know, in order to turn a profit on them, you need an energy cost of 50 cents to $1. And I'm not going to pay more for energy than I'm already paying too much for energy. I'm not going to pay double or triple that, right? But once you get to the larger plant sizes, 50 to 100 megawatts, you can drop the energy cost drastically because it's an economy of scale. So after you pay one of these facilities off, you can end up with an energy cost of around 6 cents per kilowatt hour. Before you pay it off, it's around 22 cents. Well, that's, you know, 2/3 of what I currently pay. Now, replacing Kahe, since we already did that example, 650 megawatts would cost us around $5 billion. And because this is a firm supply, you don't need the batteries. So OTEC is our only viable non-carbon-based energy source that can solve the Oahu problem. You know, otherwise we're going to be burning carbon and we're going to miss our 2045 goal. So as the only viable energy source, why aren't we doing this? It comes to the chicken or the egg. You know, we have to build a small plant before the large plant. So let's see if we can apply that same model for curtailment to the egg problem. Let's build one of these small ones. You know, now we have a lot of great data from the last 5-6 years when the Bitcoin mining industry really matured. And I consulted with Richard Argall, the senior engineer from Mackay Ocean Engineering, on this. And because no one's going to be able to pay 50 cents to $1 for it, the idea is you can just not connect it to the grid. And you can use 100% of that energy for mining. Because the idea is you just have to show that one of these things works at scale. And from personal communication, it is possible to integrate the Bitcoin mining directly into the cooling stream. So you can eliminate almost half of your operational expense for Bitcoin mining, meaning that OTEC, in theory, is the most efficient way to produce Bitcoin. it's cold all year round. You don't have to worry about summer coming and cooling costs. You can cool them all the time. And because we don't have to connect it to the grid and all that energy is stranded, we can have one of these things floating in international waters. This saves, many years off the lead time permitting process, and we can float this thing, one of these offshore floating facilities to the most efficient place on Earth for them. So, Hawaii, it's possible to do here, but there are more efficient places to do it where the temperature difference is even greater. So we applied that same model for curtailment to this. And you can see on the rows here are going to be the plant sizes, 10, 5, and 1.35. And on the columns are going to be your start dates for mining. Now, this green line is going to be your initial capex, how much it costs to just build it. And it's going to be the same between each of these graphs. Your blue line is going to be your loan obligations plus your OPEX, and the orange line is going to be your HODL method. Essentially, as long as the orange line, the area under the orange line is positive above this blue line, these things work and they're profitable. And you can see that had you started in 2016 or 2017, the 10 and the 5s would have paid themselves off already. So this is really one of the first, profitable ways to actually make one of these things work. And remember, OTEC is the only way to solve our Oahu problem. It's the only viable non-carbon source. So what would solving the Oahu problem look like? Well, we're going to need an all of the above approach. We're going to need wind, exploit all of our wind, our wave, and our solar that we can. And if you were to tie Maui and Oahu, we could get access to that geo, but I'm doubtful on that. We still need battery storage, as much of it as we can do, and we're going to need a number of 100 megawatt OTEC plant ships, I'd say around 10. And so the idea is, instead of avoiding curtailment, if we can guarantee it and concentrate the excess energy into the most profitable mining method known to man, we can use that to assist in our transition. So let's look at building 10 of these OTEC plant ships at a cost of around $8 billion. If we can guarantee a 25% curtailment rate and around 75% of that energy going to a grid sale at around 22 cents per kilowatt hour before we pay it off, you can see the same model here. Blue line is your loan obligations and OPEX. Green line is going to be your CAPEX, and the orange line being your HODL method. This orange line has, throughout Bitcoin's mining history, has followed this blue line. And so this would be the ideal solution. There's lots of talk. I've heard lots of people call me talking about, let's mine with geothermal in Hawaii, or, El Salvador is mining with geothermal now, and Iceland has been mining with geothermal for a long time. I say, no Bitcoin volcano, let's do Bitcoin ocean. So in conclusion, Hawaii has a virtually unlimited natural energy resources, yet we currently and will continue to rely on carbon-based energy and pay the highest prices in the nation. The simple reason why is that fossil fuels are just more profitable. But the inherent economics of Bitcoin mining perfectly overlap with the renewable energy, creating a natural incentive profit motive to build out renewable energy. And unlike other states that can simply export their excess energy to their neighbors, ours is totally stranded. Using Bitcoin mining, we can harness the power of the wind, the waves, volcanoes, sun, ocean into economic energy and use that economic energy to fuel our transition. And in the process, we would create an entirely new major industry in the state that brings money into the state and then brings the cost of energy down. Bitcoin is the only vehicle that will get us to our 2045 goal. and it'll do so faster, cheaper, and more efficiently than anything proposed to date. People have proposed, using this excess energy to produce ammonia or liquid hydrogen, but I'm not aware of any factory outside besides Bitcoin that can be, turned on and off instantly. You can't just call up your workforce and say, hey, we have excess energy today, come in. That's just not going to work. Bitcoin is the only dispatchable demand buyer of last resort that's feasible. So what can you do? For our legislator friends, you can integrate dispatchable Bitcoin mining into our integrated demand response portfolio plan. We can incentivize more curtailed energy. Instead of disincentivizing it, let's generate as much energy as possible, converting all the excess into economic energy. You can do that by reopening the NEM program. There's a lot of talk on the Hill about an infrastructure plan and infrastructure spending. Well, OTEC is the best investment that we could make. You could provide direct funding or subsidies or match private investment into local OTEC development, as it is our only viable method. Form a working group. If you're in the energy community, investigate curtailed energy Bitcoin mining. If you're spending money to throw energy away, why not turn it into revenue? You can combine, we're building a lot of storage, so combining our curtailment and storage forecasting, we can do this all day, generate Bitcoin revenue all day. If you're in the business community, looking at renewable energy and Bitcoin mining is the best investment opportunity in the state in quite some time. Iceland, at one point, the small island of Iceland made up 9% of all Bitcoin mining in the world, just using their excess energy to export it. We can do the same thing here. And if you're in the general population, well, contact your legislatures. This talk is being recorded, so send this on to them. And education, of course. We have, I've listed a lot of sources here. Come visit us at our website, and you can learn more or contact me. I'd love to talk more about this. So thank you very much. All right. So I think moving on to questions.
Thank you very much, Nathaniel. We've only got a few minutes left, but we do have a couple of questions, and one is one that I was going to present to you. So let's start there. Isn't all this planning based on the assumption that Bitcoin's price will continue to go up? I mean, some of your models look at going back to 2016 when a Bitcoin was like, I don't know, $100. So of course, with it being at $40,000-$50,000 now, that looks great. But we've also seen a lot of volatility. We've always seen volatility in the Bitcoin price. What if there's a black swan event that happens with Bitcoin and it just drops out? Then what?
So, like I mentioned, the size of the haystack gets smaller. Okay. Now, with OTEC specifically and curtailed energy, you have a cost of, a very low marginal cost. Now, if the price goes down and mining is still difficult, you have people around the world mining with prices of energy 10 cents per kilowatt hour, 12 cents per kilowatt hour. They're going to fall off first. But because curtailed energy by definition is waste, you can continue to mine with that waste energy because any amount of recouped cost is going to be better than zero. So. And you can see even in these models, you have prices falling down from, I think, from here to here and then falling here. It'll always end up averaging around this line. And because of Bitcoin's finite supply, 21 million, you can, it's not going to be found for another 100 years. OTEC will be the most efficient way to do it, and it can do it at a lower cost than just about anyone around the world.
Well, I'm definitely excited about that general technology. We have a question. Oh, Kevin Young had a similar question that we just asked. But another question is about the batteries. You basically kind of discount their capability. Is it simply because we'd be talking about batteries on a scale that would cover the entire island of Oahu or something?
Yeah, so in order
Bitcoin
to
doesn't
fill
serve
up
as a
those
battery?
batteries, if you're, like I said, if you're using all the energy output from a solar panel or from a wind turbine, those batteries are going, in order to fill them up, you're going to have that excess energy. And in order to meet reserve requirements, you're going to end up with even more curtailed energy to guarantee that those storage, those batteries or the pumped hydro is going to be full for when the sun is not shining, right?
Oh,
You're
right.
always
You had the
going to
6x. You had the 6x thing early on. Yeah. Okay. Correct.
yes. So
Um, Fantastic. Maybe one more question. Uh, let's see. Well, let's get to the most important one because we do need to wrap up, and it would allow people to get the answers to their questions from you after this event. Virendra wants to know your contact information. Can you bring us back to your first slide, please?
sure.
As he's putting that on screen, I should say we have come to the end of the session, and I'd like to thank everybody for attending. And thank you, Nathaniel, for your time today. I learned a lot, not just about Bitcoin, really, but actually about energy generation.